Okay, so I'm going to pick up where I left off because I ran out of time. And so just to recap, who watched part one, this is part one. I have x1 is the position of the ramp, s is the position of the block down the ramp. I need to find the kinetic energy, and I need to find the potential energy. Okay, and there's two variables. So the two variables are x1 and s. The trick here was the kinetic energy of this one, because I need to find the kinetic energy, the real kinetic energy. I can't just use s, because s is measured with respect to the top of the ramp, but the ramp moves. So if I write this in terms of real x and y coordinates, I can take the derivative to find the real velocities. And that's what I did here. So here's my kinetic energy, there's my potential energy. And so now I'm going to proceed from there. I'm going to find the Lagrangian, which is just this minus that, and then I'm going to find my derivative. So let's start up here. I'm going to put the Lagrangian, write it out. 1/2 m1 x1 dot squared plus 1/2 m2, just copying this, and this is going to be, I'm going to write it as x1 dot squared plus s dot squared plus 2 x1 dot s dot cosine alpha, and then minus this m2g c minus s sine alpha. I hope that fits on the screen. If not, it's okay, because we're gonna figure it out. Okay, so now I'm going to do, here's my Lagrange equation for x1. Okay, so I need to take the partial of L with respect to x1. I need to take the partial of L with respect to x1 dot, and then take the derivative of that. Okay, so this one's pretty easy. Let's take the partial of L with respect to x1 and look through here where I have x1 and I don't. So all of this is like a constant, so I get 0. So the partial of L with respect to x1 equals 0. Okay, now let's do the partial of L with respect to x1 dot. There's 1. So I get the derivative of x1 dot squared, the partial with respect to x dot, it's going to be 2 times 1/2 times m1 times x1 dot. So I just get m1 x1 dot. Now up here I have another 1/2 m2 x1 dot squared, so I get plus m2 x1 dot. That doesn't have an x1 dot. This one's going to be, okay, I have a 1/2 times a 2. So those cancel. I have m2 x1 dot s dot cosine alpha. So the partial of that with respect to x1 dot is just going to be m2 s dot cosine alpha. And there's no other terms. Okay. So now I need to, I can simplify this. I can factor out x1 dot m1 plus m2 plus m2 s dot cosine alpha. Now I need to take the derivative of this with respect to t. The derivative, not the partial. Okay, so what depends on time? That depends on time, and that depends on time. So those, I have to do real derivatives. Okay, so let me write that out. d dt partial of L with respect to x1 dot is going to be equal to, well here, that's a constant. Take the derivative of x1 dot with respect to t, I get x1 double dot. x1 double dot m1 plus m2. Take the derivative of this, again, alpha is a constant and m2 is a constant. So I just get the derivative of s dot with respect to time is s double dot. So I'm going to write this as plus s double dot m2 cosine alpha. And so since that is equal to 0, then this has to be equal to 0. So this has to be equal to 0. Let's see, for now I'm just going to solve this for x1 dot. So let's just solve this for x1 dot double dot. It's going to be equal to negative s double dot m2 cosine alpha over m1 plus m2. That's important. Okay. Also, you'll notice that if the acceleration of this one is that way, the acceleration of this one is it's going to be negative and be that way. So if one of them is positive, one's negative. That makes sense, okay, based on the way I have these things. You can even do some serious things. Well, we won't do it right now. Well, we could. If I solve this for s double dot and let m1 go to really, really high, we should get well, we'll do that in the next part. Let me write this up here, and then I can erase it, because we need it for later. So x1 double dot equals s double dot m2 cosine alpha, all of that over m1 plus m2. So now I can erase the rest of the stuff. Okay. And there might be an error in there, but the idea is legit. Okay, so now I'm going to do the same thing for s. So I'm going to change these variables to partial of L with respect to x, s, and partial of L with respect to x, s dot. Partial of L with respect to s equals no s, no s, no s, no s. There's an s right there. So I have negative mg times negative s sine alpha. I take the partial with respect to s, and I'm going to get positive m2g sine alpha. That's it. Okay, now let's do the partial of L with respect to s dot, so we can take the derivative. No s dot, blah, blah, blah. This one right here, I'm going to get, I bring down the 2, I get m2 s dot. So it's s dot squared. Here's another one, I'm going to get, that 1/2 cancels with that 2. I get m2 x1 dot cosine alpha. And that's it. No more, okay. So now I can take the derivative of that, the derivative with respect to t of L, partial of L with respect to s dot. It's going to be, that one's pretty easy, m2 s double dot, and that one's pretty easy too, plus m2 x1 double dot cosine alpha. And so now I can put this together. This minus this equals 0. So I get m2g sine of alpha minus m2 s double dot minus m2 x1 double dot cosine alpha equals 0. So let's solve this for s double dot. Let's do that. So I get s double dot equals m2g sine alpha minus m2 x1 double dot cosine alpha, all of that over m2. I'm just feeling like I made an algebraic mistake somewhere. But it happens. Okay. I don't have a script here. Actually, I do. I worked this out beforehand. Let's see. x1 double dot minus. Okay. Oh, I got the same thing over there. Okay, I think I'm okay. Okay, so now I have an expression for s double dot. And let's put in my expression for x1 double dot in here. No, I'm not going to do that. I'm going to stop here. You could do that. I could put this in there and then get an expression for s1, s double dot. I'll let you do that. But you should check, because like I said, we know certain cases. I know that if m1 gets very large compared to m2, then this block will essentially stay there. And the acceleration down the plane should be g sine alpha. And so hopefully you can see that when you get that out of here. What else can you do? Once you get s double dot, you can find s double dot when s equals this. You can put in some values and get the velocity of it when it gets down to the bottom, and get the velocity of this when that gets to the bottom. And you should be able to show that energy is conserved and momentum is conserved. Okay, so that's pretty cool. Okay, so that took a little bit longer than I wanted to, but it's a great problem and it's a great example.